As usual, I'm going to record today's meeting and then I will upload on the YouTube. And let's see how many students here. We have 15 students. Okay, good. So today my schedule will be talking about the linear motion. I will do some derivation about the equation. Then I will spend a couple minutes talking about the homework due yesterday. And if you find the homework due yesterday is at midnight on Tuesday, that's a mistake. But you can still upload your submission. There's no punishment if you submit the homework a little bit late. Okay, so the linear motion actually we're talking about today is a mass point moving straight. So if we have an object and we can treat the object as a point, if we don't care about the shape or if we don't care about the deformation during the motion, we only need to know where the center point of this object. So we treat the object as a mass point. And if this mass point moves straight with any speed, then if it moves straight from place A to place B, we call such motion as the linear motion. So that means the trajectory is a line. We will talk about the trajectory, which is a circle or the projectile circle or other motions next week. But today we only talk about the linear motion. And the linear motion is a fundamental physics, and this is a topic help us to understand the complicated motion. But before we go to the complicated things, we need to know the fundamental motion. The linear motion will be a motion with a straight trajectory. And when we talk about the motion, we have several parameters need to figure out. We have 5 parameters to describe a motion. The first one will be the time. Time means how long does it take to finish this motion. We have color. So we have time. So time is the duration of this motion, and the unit of time is second. Sometimes you will find a minute or hour for when the description said about the time. But when we see the minute or the hour, we have to convert into the second, because the second is the standard unit. And all the equations, at least here, are based on the standard unit. So if you see an hour or minute, please convert into the second. Then we can make sure every unit is a standard, then we won't get the mistake. And for the time, we have the notation. We label the time as a little t. And sometimes you will see a delta t. They are the same thing. So t or delta t are the notation for the time. Okay, this is the first one. The second parameter and the third parameter is about the speed. We call the velocity. And the velocity, we have 2 velocities, the initial velocity and the instant velocity or the final velocity. The velocity here is, I use v, the little v, to represent the velocity. With a 0, this is initial velocity. Without the 0, this is a final velocity or instant velocity. And the unit for the both are meter per second. If you see miles per hour or kilometer per hour, we need to convert into meter per second. This is velocity. and the velocity describes how fast for the object during the motion. And the velocity might be a constant or might not be a constant, depends on the acceleration. So the next one we are going to talk about is a displacement. Here we use how far does the motion travel in the straight forward. So we have displacement. If the displacement is in the horizontal direction, we use X to represent displacement. If it's vertical, we use Y. They are all displacement. And the displacement has a unit of meter. It's a standard unit. Also, when we talk about velocity and displacement, they are vector. So for linear motion, there are only two direction, positive and negative. So for every motion at the beginning, we need to define which direction is positive. So we define right is positive or up is positive. After the definition is done, we cannot change it. You can also define in the opposite way. You define the right is positive, the left is positive and the right is negative. That doesn't matter. It depends on your preference. Someone like the positive to the down and negative up. So doesn't matter. But after you've done the definition, you cannot change it. So for the whole problem. Okay, this is displacement. And the final, we have another parameter is acceleration. We use little a to represent the acceleration. The acceleration describes how fast the speed change. And in this class, we are talking about a constant acceleration or a uniform acceleration. So all the equation in this class, today's class, is uniform acceleration. So if the acceleration is not uniform, we cannot use the equation listed here. Okay, so acceleration in this class is a lecture. A is a constant. And the unit for the acceleration is meter per second square. Okay, so that means we have 5 parameters to describe the linear motion: time, initial velocity, final velocity, displacement, and acceleration. Ideally, if you know 3 of them, if you know 3 parameters, any 3 parameters, you can solve the rest 2. And how to solve the rest 2 parameters are equation here. Those equations tell us how to solve the parameter if we know 3 of them. And you can check those 4 equations. Each equation only contains 4 parameters. For example, the first equation, you won't see displacement. There's no displacement, right? We have initial velocity, final velocity, acceleration, and time. There's no displacement. That means if you don't care about displacement and you know 3 parameters that you want to solve time or you want to solve velocity, you can use the first equation. The second equation, there's no final velocity. You have initial velocity, time, acceleration, and the displacement, right? That means if you don't care about the final velocity, you're going to use the second equation. The third equation is no time. So if the motion is too quick and you didn't prepare a timer to record the time, then you use this equation. The final one, there's no acceleration. If there's no acceleration, you are going to pick up the fourth equation. So that means if you know 3 parameters, you can solve 1 parameter by 1 equation. Then you have 4 parameters, then you can solve the final 5. Okay. Then let me give you some derivation why and this equations is true and why we need these equations. The first one, let me talk about the first equation. This first equation, we don't have displacement. And if you're familiar with the definition of acceleration, this is some simplification of acceleration. So let's go back to the definition of acceleration. If the acceleration is a constant, change another color, is a constant, then the definition of acceleration will be the change velocity over change time. The acceleration is the change rate of the velocity, right? So if the a is a constant, then we can use this definition to get a equal to the final velocity minus the initial velocity divided by the duration. Then we have the final velocity equivalent to the initial velocity plus acceleration multiplied by time. So this is just some simple math from the definition of acceleration. Then we get the first equation. Here, both v and a has a direction. That means if a is positive, then you will find that the final velocity is larger than the initial velocity. Then we will have a VT graph as linear increase. And if the a is negative, then you will have the final velocity smaller than the v0. Then the curve will be decreasing. Right? And if the curve goes to 0, that means the velocity goes to 0. And if the velocity goes to negative, that means this motion return. Okay. The final one is if a is 0, that means this is a constant velocity, v equal to v0. Then we will have a constant and flat curve in the VT graph. Okay, this is the first equation. If you have any question, you can stop me and I will give you more explanation. Next one, we're going to talk about the last equation. The last equation, you can find that there's no acceleration. This is the definition of average velocity. Think about that. If a is a constant, then in the VT diagram, we have a linear line. Okay, then we know the average velocity. Use V bar to be written as the total displacement over time. And if A is a constant, then we know the total displacement over total time could be written in another way. The average velocity is equal to the initial velocity plus the final velocity over 2. This is only apply for the case when acceleration is a constant. A is a constant. If A is not constant, they are not equivalent. If A is not a constant, V bar is not equal to V naught plus V over 2. But the definition of average velocity is always correct. This doesn't depend on the motion or the acceleration. If we have any motion, any trajectory, any acceleration, the average velocity is equivalent to the total displacement over total time. Okay, and if we have a constant acceleration, then we will have the average velocity equal to the total displacement over duration. Then let's move t on the right side, on the left side. On the left side, then we have the displacement equivalent to the here V average times delta t. Then here is 1/2 V0 plus V times t. So this is how we get the last equation. This is just a definition of average velocity. And from the VT diagram, we also know the displacement in this duration is equivalent to the area between the curve and the time axis. Right? The displacement is the area. From this geometry, we know the area is equivalent to the initial velocity, final velocity, and duration. We have initial velocity plus the final velocity times the duration over 2. So that means this equation is from the area of the VT curve. And we know V0 plus V over 2 is average velocity. So they should be the same thing. Okay, so this is the derivation for the last equation. Then let me go back to the second equation. The second equation is also very important. That means if we don't know the final velocity, we know the initial velocity, duration, acceleration. How do we get displacement? So the derivation for the second equation is from the first equation and the last equation. So let me do the derivation. So from the first equation, we have the velocity equal to the 0, V0 plus AT. And we want to remove the final velocity. So how to remove the final velocity? We have the fourth equation, delta x equivalent to 1/2 V initial velocity, final velocity, and duration. Then let's plug in this one into here. We're going to replace the final velocity. So we have delta x equal 1/2 V0 plus V0 plus AT. So we just replace V by V0 plus AT. And let's do the simplification. We have 1/2 20 2v0 plus at times t. Then this is equivalent to vt v0 times t plus 1/2 at squared. Okay, so this is the relation between the displacement and the time. And you can find that this is not a linear relation. The displacement and time has a relation of t squared. So there's a parabolic curve. So if we draw the xt diagram, the graph will show you a curve. This curve is a parabolic curve. This is proportional to the at squared. Okay. This is xt graph. And do you have any question? Okay, let me move on. The next one I'm going to talk about is the third equation. Third equation said if we don't know time, can we get the relationship between the velocity, acceleration, and displacement? The same thing, we are going to use the first equation and the last equation. We're going to replace time. So from the first equation, we know the time is equals the final velocity over the initial velocity divided by acceleration. And for the last one, we have displacement equals 1/2 final velocity, initial velocity multiplied by time. So the time we are going to replace by the first equation. So we have v minus v0 divided by time. Okay, let's do the simplification. We will have 1/2, and the numerator will be v times v plus v times v0 minus v times v0 plus minus v0 squared, okay, divided by acceleration. And you will find that v0, v times v0 just cancel. So we have 1/2a times v squared minus v0 squared. Okay, so let's multiply the 2a on the left side. We have v squared subtraction equals 2 times acceleration and displacement. Okay, so this is a derivation for the third equation. That means if we don't know time, then we're going to pick up this equation. Let me give you a short summary. How do we solve the problem if we have linear motion with a constant acceleration? So the first one, we are going to read the description and figure out how many parameters do we know. There are 5 parameters to describing motion. If you still remember, that will be time, initial velocity, final velocity, displacement, and acceleration. There are 5 parameters. And if we know 3 of them, and we can solve the rest of 2. Okay, then let's see. We need, hold on, this is second point. The third point, so we need 3 no parameter, 3 parameter, no parameter. This is what we know, and plus 1 unknown parameter is the parameter we're going to solve. 1 parameter that is unknown. And figure out which equation includes this 4 parameter. Find an equation including 4 parameter. Then the final step is to solve the equation. Okay, so it seems the 5 steps is not difficult, but we need to do some practice. So let's go back to the homework and let's see how the problem solving flow. First one is an envelope, the antelope moving with constant acceleration. Okay, this is very important. We're going to pick up these 4 equations and cover the distance between 2 points. We have 70 meter in 6 seconds, and it's needed at the passing the point 15 meter per second. Okay, so here we have 3 parameters. Let's figure out. The 70 meter is displacement. Use another color. This is displacement. 6 seconds is time, and the 15 meter per second is the final velocity. And we are going to solve the speed at the first point, that's the initial velocity. So that means we don't need acceleration in this question. If there's no acceleration, let's pick up which equation doesn't include acceleration. We have the number 2.14. This equation doesn't include acceleration. So let me copy here. The displacement equals 1/2 v0 plus v times t. This is the equation we're going to use. The displacement is 70, and the velocity here is unknown. We keep here, and the final velocity is 15 meter per second. Time is 6 seconds. Okay, so the initial velocity we can solve. Let's see what's the value of the velocity. Let me see. So the velocity is 8.33 meter per second. Okay, this is part A. Part B, the acceleration. Acceleration, let's see, because we already know 4 parameters. So we just need to pick up any equation includes acceleration. Let's use the first equation. The first equation is easy, right? So we have final initial velocity and time. So we have final velocity, initial velocity, and time. We have final is 15 meter per second, initial is 8.33 meter per second plus a times 6 seconds. So the acceleration is solved. Let's see, what's the acceleration? That's 1.11 meter per second square. Okay, do you have any question? Okay, let me move on. And a faster pitch. There's a baseball player and throw a ball. This ball has a final speed 45 meters per second, and set this ball contact with the pitcher's hand with 1.5 meter. We need 3 parameters. Here we only have 2 parameters. That means there is 1 parameter hidden in the description. So where is the hidden parameter? So we can assume this baseball in the pitcher's hand starting from the 0 velocity. The initial velocity is 0. This is very important because this is reasonable assumption. And this baseball starts from 0 and accelerated by the pitcher, and the final velocity is 45. Now with this assumption, we have 3 parameters in total. So we have displacement 1.5 meter, we have initial velocity, final velocity, and then what's the acceleration? So we need to find an equation include initial velocity, final velocity, displacement, and acceleration. So which equation contains this 4 parameters? So we need an equation without time. Okay, we're going to pick up this one without time. So we have final velocity equals initial velocity plus 2ax. Okay, this equation doesn't include time. Okay, let's see. Final velocity 45 meter per second square, and 0 square plus 2 times acceleration is the parameter we're looking for. Displacement is 1.5 meter. So we can solve. Acceleration is very large, 675 meter per second square. Okay, part B. Part B, time. Okay, we need an equation include time. So let's use the first equation. Final velocity, initial velocity plus AT. This is the easiest equation in those 4 equations. So the first one, let's figure out the final velocity 45, 0 plus a 675 multiplied by time. So the time is, let me see how much, 0, 0, 0, 6, 7 seconds. So you might have a question, how many significant figures should I keep? Let me see. When I do the grading, I don't consider the significant figures you have, but to make the significant figures uniform with the description, let's figure out, because there are 3 significant figures, there are 3, so let's keep 3. So if keep 3, it will be 6, 7. Actually, it doesn't matter. I don't take credit off if you have 2 or 4 significant figures. But this is very important when you do the experiment. So experiment, you have to make every parameter uniform. But for the recitation, I don't mind. Do you have any question? If there's no question, let's move to the next question. There is an egg, okay, and it says this egg is thrown vertically, and it says the egg just return and goes down past a point 30 meters below its starting point 5 seconds after leave the thrower's hand. Okay, let me draw the diagram. And we have egg. Okay, this is throw vertically, throw up, then the reach to the highest point, then goes down. And it takes 5 seconds to reach a position 30 meters below the starting point. So from starting point to the final point, there are 30 meters. And it takes 5 seconds. 5 seconds to reach this point. Okay. This is description. Then part A, what's the initial speed of the egg? We need 3 parameters to figure out, but we only have 2 parameters. One is the displacement. The other is time. So do we miss any parameter here, or is there any parameter hidden in the description? So let's go back to the first sentence. It says thrown nearly vertically. That means there is an acceleration caused by the gravity, right? The gravity gives us an acceleration g, negative 9.8 meters per second squared. So this is a constant acceleration. And the reason I use a negative sign in front of this number because I define the upward is positive and the gravity goes down. So we have a negative sign in front of 9.8. Okay, let's see. We have displacement. The displacement is from the starting point to the ending point. Displacement goes down. Okay, this is displacement. And don't use this as a displacement. This is a distance. This is displacement. Okay, so be careful, they're different. So let's solve the problem. We have displacement, we have time, and we have acceleration. And we need to know the initial speed. So we need an equation without final velocity. So the equation will be part A, displacement equal to initial velocity multiplied by time plus 1/2 a t squared. Okay, let's see. The displacement goes down, so we have negative sign in front of 30 meters. Velocity is unknown. Time 5 seconds. Close. 5 seconds plus 1/2, and let me see, the gravitational acceleration is negative 9.8 meters per second square multiplied by time 5 square. Okay, so we can solve the initial velocity. The initial velocity, let me check the solution, that will be 18.5 meters per second. Okay. Part B, how high does it rise above its starting point? How high? So we're going to find the highest point, this point. We're going to find the displacement from initial if I label this as h, the h is what we're looking for. This is displacement from the initial point to the highest point. And at the highest point, we have a hidden condition. That means at the highest point, velocity is 0. This is very important. If there's a non-zero velocity at the highest point, that means the egg can still moving up. So if this is the highest point, that means the velocity goes to 0. Then the velocity will turn to negative. That means the egg is going to drop down. Okay, so we have final velocity and we have initial velocity and we have acceleration. So to solve the height as a displacement, we're going to looking for equation without time. Without time, that will be the equation velocity square equivalent to the initial velocity square plus 2 times ax. Okay, so the initial velocity is 0. So drop down this one. Oh, hold on. No. The final velocity is 0. So this is 0. So we can solve the x. X here is height. Height will be 17.5 meter. Okay, part C, what's the magnitude of velocity at the highest point? 0. Part D, what's the magnitude and direction of acceleration? That's negative 9.8 meter per second square, and the direction goes down. And the last one, E, sketch AT diagram, VT graphs, and YT graphs. So let me draw the diagram. Acceleration as a function of time, velocity as a function of time, and displacement as a function of time. Okay, the acceleration is negative and it's constant, so it's a flat curve. It's negative 9.8. Okay, and the velocity, at the beginning, the velocity is positive, it goes up, and then it reaches to the 0, then turns to negative, and it's linear. And for the y, we know the displacement has a function of t squared. So this is a parabolic curve. I start from 0 point and reach to the maximum point. The maximum point is how high? 17.5 meter. And it dropped down. And the final point is negative 30. Okay, this is a solution for this problem. And we have one more questions. I didn't find problem from your homework, so this is very easy. But I want to show you what does this mean by S wave and P wave. So for the wave, we have two kind of waves. I show you the figure. My figure. Here you can see there are two kind of waves. What's the difference of these two waves? Given notation. So for the first wave, we call transverse wave, or we can call this S wave. Hold on, I get this right. No. Yeah, this is S wave. Transverse wave is called S wave. And the longitudinal wave is called P wave. And you can find the difference is that the transverse wave has oscillation up down, right? The oscillation goes up and down, and the traveling speed is horizontal. This is a wave traveling speed, travel, and the oscillation is perpendicular to the speed of traveling. But if you take a look of the longitudinal wave, you find the oscillation is horizontal, right? This is oscillation. And the traveling speed is also in the horizontal direction. So that means the oscillation and the travel speed are parallel. This is called longitudinal wave. And you can also find that the longitudinal wave usually is larger than the transverse wave. So we have the P wave has a larger speed, as 6.5 meter per second, kilometer per second, and the S wave has a little bit smaller speed, at 3.5 kilometer per second. And usually in the air or in the water, the liquid or in the gas, you can find the longitudinal wave. So the longitudinal wave can in the air, in the water, or in the solid, because the directions are parallel. But if you want to have a transverse wave, the transverse wave needs a very big shear force, because the oscillation is up and down. But if an up-down molecule want to impact another molecule close to itself, the shear force is very large. But the water and air cannot provide such big shear force. So this wave only can find in the solid or on the surface of the liquid, surface of the water. So this is the wave. And you can also find some video on the YouTube and to see the introduction of the wave. So I think this is all the things I want to talk today. And let me stop the sharing. So one more thing I'm going to talk today is, hold on. Is there any question I see on the chat? Hold on. So will this lecture be uploaded? Yeah, I'm going to record this